Okay, good. So yeah, uh, before we talked about segmentation in the last lecture, and what was segmentation about? It was variable size spaces, right? So space is divided into variable size chunks, and this we saw that like led to fragmentation, right? No matter what strategy we found, this led to fragmentation. So what about fixed size? So this is the approach that we'll be seeing today, and this is the approach called paging. So these fixed size chunks will be called pages, and the physical memory will be array of fixed size slots, and they will be called page frames. So pages are the virtual memory's small parts, the chunks of virtual memory of fixed size, and in physical memory, the spaces that we get by dividing the physical memory into fixed size chunks. It's called page frames. Okay, so just a small, very trivial example. So suppose suppose only 64 byte address space, okay, and divided into 16 byte pages. So we have now 32, 16, 48, 0. So this is the virtual address space of the process. So this is page 0, page 1, page 2, and page 3. Okay. And let's say that the physical memory is 128 bytes. So how many page frames will be there? Because page frame size will have to be the same size as the page. So 16 byte page frames. So they'll have 8 page frames. Okay. 16 bytes each. So how will this look? The physical memory now. So 64, 96, 128, Okay. And suppose here is the OS in the first place. Then suppose this is unused. Then here is the page 3, page 0. Then again, this is 3, page 2. So this is how it will look. So now the virtual memory is divided into four parts, and those four parts are put anywhere in the physical memory, like here on on these slots. And so this is the main concept that now the virtual memory will be divided into equal chunks, and they all will be placed in the physical memory. Right? Okay. So what is the advantage of doing such a thing? So there are two major advantages. First is flexibility. Now, since it is divided into like equal size slices, then we don't really need to care, how the heap and stack grow, and how the process uses, just allot this, and then the process can use any way the space as it wants. Oh, yes, not need to know whether the heap stack grow positively, etc. Okay. And another advantage is simplicity. And why is it simple? Because in segmentation, we saw that there were variable size spaces. Then OS will have to find a strategy that, okay, whether we do first fit, uh, worst fit, best fit, what to do. Here, OS can just have a free list of available frames. Okay. Now, so this is the in a nutshell what paging is, that instead of dividing it segment wise, that this is the heap, this is the code, this is the stack. Now just chop off the virtual memory into equal parts and put that in the physical memory. Okay, but then now the OS needs to know that which page is where. Okay. So to remember this, OS uses a data structure named page table. Okay. And this is a per process data structure. What does that mean? That for every process, we'll have one instance of this data structure. Okay. So what is the use? Translation of addresses. from virtual one to physical one. Okay, good. Now, like for this example, what would the page table have? So page 0 is mapped to, so let's call these page frames, let's give these page frames also numbers. So this is page frame 0, page frame 1, page frame 2. Yeah. So 0th is mapped to 3 and so on. So here something like, so this page table for the example, the page table looks like following, which is virtual page 0 to physical frame 3, and we'll shorten it at virtual page 1 to physical frame 7, virtual page 2 to physical frame 5, and virtual page 3 to physical frame 2. Okay. So as I said, for each process, we'll have one page table because we need to know where in the physical memory the pages of this process lie. Okay. So now let's see an example that how such a address translation might work. So suppose we have something like an assembly instruction like move L, some virtual address, and we want to load the content of this virtual address to support suppose the register EAX. Okay, so load content of virtual address to EAX register. Okay. So now to perform this, every virtual address will be divided into two parts. So first will be called virtual page number. Or VPN, and the other will be called offset. Okay, so virtual page number is basically when you divide the address space into certain parts, then the virtual page number will tell you which part you are in, and the offset tells how much in that part you have to go. So here our virtual address space was 64 bytes in example. So how long will be the virtual address? How long will be the virtual address? How many bits?
6 bits.
Bits. And out of this, each page is of 16 bytes. So how long will be the segment?
4 bits.
4-bit segment. And now since there are 4 pages, so 2 bits for the VPN. Okay, so this. So let's say virtual address 0 to virtual address. So this is going to be the VPN, virtual page number, and these are going to be the offset. Okay, good. So suppose the specific instruction was move L 21, comma TX. Okay, suppose this was the instruction. So now first you write 21 in binary, which is 010101 8 4. So yeah, 16, 4 and 1. Yeah. And then now, so this becomes your 010101. So now this, as I said, will be the VPN. This will be the offset. So this is 1 and this is 5. So offset is going to be 5. 1 is going to be the VPN. So this means that first virtual page and 5th byte in that virtual page. Okay. So how will the address translation work? It will take this so it will look at the VPN and this is the offset. So now the address translation will take the VPN map it to a physical frame. Yeah, in our case, this was 7 for first, and just append it with the offset. Okay, so this is going to be 111 because the first page was mapped to the 7th frame here. So this will take it to 7. So this was 01 will go to 7 and then 0101 will come as it is. So this will be the desired address and this will translate to 117. Okay, so the offset stays the same. Okay. So we'll see it like in slightly more detail how exactly it's done. And there are many questions now, like so this is just like in a nutshell how the this whole mechanism works. And now we'll go into detail that, okay, so there are some questions. First is, where are these page tables? How big are they? And what do they contain? And also, does these paging overheads, does it affect the performance? Okay. So we'll consider these questions one by one and see what are the answers to them. Okay. So first thing, let's look at where our page table stored. And also how large are they? So let's consider these two together. Okay. So first thing is can be very large. How? Let's see. Like let's do some like back of the envelope calculation. So suppose we have 32-bit address space, which is very common. So and suppose we have 4 KB pages. Okay. So 4 KB pages will take how many bits? The offset. So suppose a page is of size 4 KB, then how long will be the offset?
12 bits.
12 bits. So 10 bits is 1 KB, so 2 more for 4 KB. And so remaining now, so 12 bits offset. So now with these 12 bits, the remaining 20 bits is going to be VPN. Okay. So how many? So OS will so have to manage how many virtual pages? 2 to the 20 translations. Right? And what is 2 to the 20? It's 4M, right? Sorry, 1M. And suppose one address translation or one entry in the page table takes 4 bytes, then the memory needed for page table of one process is going to be 4 MB. Right? So this is for each page table. And if 100 processes, which is not very large, then 400 MB is just going for page tables only. Okay. So the thing is that page tables are big. You cannot have on-chip hardware to store. Okay, good. So since we cannot have on chip, so where do we store them? Store in memory. And which part of the memory? Let's say that the part which is managed by the OS. Okay. So this is one thing. So the takeaway of this was that so here now in fact, so the picture that we had here in addition to the OS plus you can say page tables also. So the takeaway was that page tables can be huge, and that is why we need to store them in memory. We cannot have on-chip hardware which like store the whole of a page table. And yeah, good. Now the other question was, what is there in a page table? So in a basic sense, what is a page table? Page table is a data structure that maps virtual addresses, in particular here page VPNs, let's say virtual page numbers, to physical addresses. In particular, physical page frames, right? Because the physical memory is divided into page frames and the virtual memory is divided into just pages, right? So, what is the simplest way to store such a thing? It's called a linear page table. And just an array. So this is just an array, and what does this array have? The index is going to be the virtual page numbers of the process, and the content will have the physical frame number. Okay. So this is what our data structure is going to look like. I mean, so this is a very simple data structure, and it like consumes a lot of memory because for every table entry, for every VPN, you need to have something and so on. So there are some other data structures also which are used to have this thing, but we'll not be discussing that here. We'll come to them later. So for today, let's assume that it is stored in an array. The page table is an array, and the index is the virtual page numbers, and the content is going to be the physical page frame numbers. Okay, good. And now, in addition to these, so and now this thing is called the content. One entry is called page table entry. Okay. So it will have, of course, it will have PFN. But also apart from PFN, also it will have some info. So what else? So it has some bits actually. So let's see some common bits and then which are there generally. So first is called a valid bit. So this is just for to know whether a translation is valid. And this bit is very important in like now. So we saw that the page tables are big because they have a lot of entries. So we saw that they have like about 1 million entries for these pages, right? For 4 KB pages and so on. So, I mean, more than that, like 1 M entries. So, now if you store all these pages also in physical memory, then it will take a lot of memory, right? So, what is going to be the idea? The idea is going to be that so when the program starts running, a lot of space in its address space is unused, right? Like we had seen that this was the address space of the process, here was code, here was heap, here was stack, and all this was unused, right? So for all these, we'll put invalid or the valid bit to be 0 for all the frames which contain only the unused space, right? And if a process tries to access PTE with valid bit 0, trap will be generated. And the OS will know that this process is trying to uh, access some memory which does not belong to it, which was actually unused. So the OS will take care of it, terminate the process. So as I said, now valid bit is crucial for maintaining sparse address spaces. Maintaining So what are sparse address spaces? What do I mean by sparse address spaces? Like this, that a lot and you want to maintain them. So what would you do? Mark unused pages as invalid. And because of that, there is no need to save them in physical memory. And you can save a lot of space. So this valid bit is quite crucial for this operation, for this reason that you only store then the valid frames which are there in the physical memory and you don't keep the invalid frames. Of course, there is going to be some protection bit. To indicate read, write, execute, access. So this, you know what it is. I'm not going to describe it in detail. Then there is something called present bit. Okay. So this is about whether the page is present in physical memory or it is on disk. Okay. So what will happen sometimes that we'll discuss in later lectures that sometimes what can happen that a page so again even after the invalid pages and so on still the physical memory might be less for all the page keeping all the pages of all the running processes. So sometimes what will happen that a page of a process might get what is called swapped out. So it was not being used by the process so frequently or whatever, and then some other page was needed for some process or for this process itself, and then they just put this page on the disk and brought something else, right? So this swapping out mechanism is needed to support address spaces larger than physical memory. So we'll come back to this, but this is a very important bit that whether this is present or not. Okay. There is one bit called dirty bit. This will indicate whether the page has been modified after being brought in memory. And then there is another bit, the last bit that we are going to discuss is called a reference bit, also called access bit. So this is going to have whether a page has been accessed. Okay. So this one is useful in determining which pages are popular and hence should be kept in memory. You should not swap them out. Okay, and this bit is needed for, as I said, page replacements or page swapping. which we'll see later. Okay. Good. So these are some of the example bits that one page table entry usually has. So the page table entry, in addition to the physical frame number, it also has these things. Okay. And there are some other things also. So now, depending on the system architecture, there can be some other bits. So if you read in the book, they show the 8.6 architecture, and then there what exactly is the, and they discuss that. But I mean, these are the main ones which are generally there in every. Okay. So this is what an address space, sorry, page table entry has. Okay, good. Now the question is, the final question was, what is the overhead? Okay. So we already know that page tables can be definitely big. Now we'll see that they can be slow also. So let's look at our earlier instruction. Move well 21% EX. Okay. And suppose the instruction has been fetched, we are only going to execute it. So what is the execute part? Load the register with content of virtual address 21. Okay. So now there are two approaches of address translation in terms of pages or page tables. So we are going for the hardware-based address translation. So now you'll see more details of how the it is done actually. So 21 has to go to 117. So this is the total. This is the final aim, which we have already calculated. But let's see what happens in the process of doing that. Okay. So the system must get. So how will the system reach 117? The system must get the content of the correct page table entry, right? From the page table. Perform the translation, and then perform the load. Okay. So for this, now the hardware must know where the page table is. Right? So for this, there is a register called page table base register, which points to the base of the page table. Okay. So contains physical address of starting location of the page table. So this is also for different processes. This register will be different. This will, like, since page table is a per process data structure, this register will point to the base of that process's page table. Okay. So now how the hardware performs this? So it does something like, so first it needs to extract the VPN. So how will the VPN be extracted? So it will first look at the virtual address and it with VPN mask. Basically, the first few bits are going to be 1, everything else is going to be 0. And then right shift it by the offset size, like number of bits in offset. Like for example, so suppose here our virtual address was 21. So as we had seen, it was 0101. Right. So now it will AND it with the VPN mask. So what is the VPN mask? 11. This is the VPN mask. This is the virtual address. What you get is 010000, and then you shift it right. 4 bits, because 4 bits is the size of the offset. To get so this is the virtual page, virtual page number. Okay. So this way the hardware gets VPN. Good. Now it wants the entry of the page table where this particular virtual page number it will find. So what is going to be the PTE address? That is going to be page table base register, as I said. Plus VPN times size of page table entry, right? So as I said that the page table here, we have assumed that it is an array which is indexed by the VPN, right? So the page table entries are going to be 0001 and they'll be indexed by that, and the size of PTE, if you multiply, then you get to the correct entry of the page table, right? So 01 here is index into the array of page table entries. Okay. Now, after that, after going to the page table entry, extract the physical frame number, then concatenate with the offset to get physical address. So if you want the hardware instruction for this, how will it do? So offset is equal to virtual address and offset mask. So what is the offset mask? Offset mask will have the first bits of the VPN 0 and the other bits to be 1. So in this case, it's going to be 0011111, right? So when you do your virtual address 010101, and with this you get the offset is 0101, right? And then physical address, if now you want, is equal to, now you take uh, the frame number, you shift it right again by number of bits in offset. And this you OR with the offset. So after shifting it left, you get this to be 010000. Your offset is 0101. Sorry, PFN was something else. PFN was, what was it? In our case, the PFN was 7. So PFN was 7. So 111. Sorry. So you get 1110000, and this you do with offset is going to be first 3 zeros, then 0101, and you get the final address 1110101. Okay, and now the hardware has the final physical address, and now it can load the data from final physical address to the register. Okay. So all this was needed for loading one value. Right? So for every memory reference, we'll have one extra memory reference. For what? So what will be this memory reference for, the extra memory reference? Anyone? No. So what I'm trying to say is that for every memory reference which is requested by the program, the system will have to do one extra memory reference. So what will be this extra memory reference for? Okay, let's see the whole. So let's look at the general process for memory reference. Okay. So first, we need to find the VPN. So VPN is equal to virtual address and we AND it with the VPN mask. Okay. And then we right shift it. Okay. And this shift, as we said, was number of bits in offset. So this is for extracting the VPN. Now the second one is going to be, now we want the page table entry address. So what is the page table entry address? That is going to be the page table base register plus VPN times size of page table entry. Okay. So this get the address of page table entry. Okay. The third step is going to be page table entry. So let's say this is a variable, page table entry is access memory. The system now needs to access that memory. At the PT address. So it fetches the entry. Then what needs to be done? It needs to check whether if valid bit false, then raise exception. Let's say seg fault. Right? Now if PT protection is equal to or access of PT protection is false, let's say. then raise some exception of protection fault that we are trying to access some memory which should not be accessed. And if everything goes well, then we go and first extract the offset is equal to virtual address and offset mask. So offset mask, as I said, will have the first few bits, the VPN bits as 0 and the offset bits as 1. The physical address is equal to the what we had, pte.pfn, the pfn value, shifted by pfn shift. And this we OR with the offset, right? And finally, we want in the register is equal to access memory of this physical address. Okay. So these are the steps involved in a memory access, right? So for every memory reference, the hardware needs to do all these things. So what I said earlier that for every memory reference, the hardware will have one extra memory reference. Now, can you see this? What does that mean? So where is the extra memory reference?
The PTE address.
Yeah, the PT address. So not the PT address, but yeah, at the PT address, from the PT address, it has to get the third step, where it has to get the entry, the pasteable entry from the PT address, and it has to fetch that to actually get the PFN, the physical frame number. So this is the extra access of memory. Okay. So as we see, and this is done for every memory reference from the process. So we saw, so for every memory reference, one extra reference. So this results in a slowdown, at least by a factor of 2. Because for every memory reference, you are doing one and then you're doing some more stuff, right? So this is one problem. So now just imagine that, okay, I mean, whatever your speed was, whatever, with whatever, it just gets halved just because of this paging thing, right? So these are the two major problems with paging. And we'll address those in first is large size and second is very slow. And we'll address this in coming lectures. So at least the basics, I hope, are clear of what paging is and how it can be implemented. What is the basics of the implementation? So all the addresses are divided into the virtual addresses are divided into page numbers and these offset and so on. So the book has one nice illustration of how many memory references are generated to which addresses and so on. So it's just like an example. So if you have a loop and so the book goes by initializing an array and basically just putting all the elements of the array to 0, and what kind of memory references are generated in that. And it's a nice example if you want to go through it and just try to understand that, okay, how these memory references are generated in terms of page tables and so on. And yeah, and also there is one additional thing, as I said, that the book also mentions the 86 architecture and what does the page table entry have in 86 architecture, and it has some additional bits if you want to have a look. And also there was this trade-off between valid bit and present bit, that you can have only one of those and the other can be inferred from the like some context or where the process where the frame is and so on. So it might be interesting to have a look at those things. But yeah, this is all I wanted to do for today. And in the next lecture, we'll do TLBs, translation looker buffers. So yeah, any questions, anything? We have some time. Like yeah, I finished like 5 minutes early. No questions? Okay, cool then. Thank you for coming. So see you on Monday. Have a nice weekend.
Thank you, sir.
Thank you, sir.